My name is José Sérgio Almeida. I'm from the Brazilian National Institute for Space Research, INPE, from São José dos Campos, São Paulo, Brazil. And today I'm going to talk about spacecraft environmental tests. Where are they applied and why they are required, the environmental tests? Mostly at three different levels. At the component level, we do screening of the components. When we purchase components for the manufacturer, they came pre-qualified roughly, or pre-qualified, but after shipping, sending and handling, we have to again do some tests with them, even they were pre-qualified. Why? Because some of them, they are qualified, but are very close to the margin to have a failure. So doing a screening of components, we stress them a little bit more. If they have to fail at the beginning of life, they can fail in the laboratory. If they are very close to fail, they will fail in our laboratory, even they were pre-qualified. So we try to do not use them anymore because they can fail during the orbit. So we can skip them. We do not use these components. We can retest them in our laboratory after shipping. We make sure we get and use all the good ones to build the spacecraft itself. The ones that are very close to failure, we can get the failure, forcing them to fail in the laboratory. So this is a component level. Then we go for the subsystem level. We use all the electronic components to build the boxes, the equipment. So then we have the box ready. The boxes are onboard computers, DC-DC converters, power supplies, all the electronics of the satellite. So we build them. But once we build them, we do the test with them as well before integrating the spacecraft, the real spacecraft. Why? Because if they have to present some failure, it's better to fail at this moment here. Because once installed inside the satellite, it's much more expensive, much more difficult, takes more time to withdraw that box from the spacecraft and do some maintenance and test it again, put it back in again. So if you have to have some failure at this phase, it's better to have, at the moment, to have all the box itself. You can see here in this picture, an electronic box inside a small vacuum chambers. Vibration, EMI/MC, and thermal vacuum tests with the box itself at this phase here, this level here, before installing and integrating to the real full model of flight spacecraft. Then when the spacecraft is completely finished, integrated, we do a full test of the complete spacecraft integrated again, once more. Then we do all the tests again, vibration test, thermal vacuum test, EMI/MC testing, all the testing, mass properties again, as a full integrated assembled spacecraft once more to make sure it's ready for flight. Why? Because we also want to make sure that the handling and manufacturing of the spacecraft was made properly according to the specification. Let's talk now about the tests to be performed in the distinct models of the spacecraft. Let's start with engineering model tests. The objectives of these tests of the engineering model are to verify the layout of the model. So you want to make sure that the building of the spacecraft was made according to the design. So I have all the compartments, all the boxes, positioning, so we want to check the layout of this. So also we can identify in these tests here, any possible interference in terms of mechanical and structural. We also can verify the communication among the subsystem. They must be corrected because we are going to have electronics in this model tested here. So we can perform the first electronic test on the subsystem as integration configuration. This is an electronic model. Doing this, we can identify possible problems with the design in terms of operation with other spacecraft subsystems because we are testing, verifying the electronics here. Doing that, in this model, we can also validate the equipment we use to talk to the spacecraft, what we call EGSE, or Electrical Ground Support Equipment. We can validate this, all the equipments we put around the spacecraft. And also, as we have a sequence of tests, we can validate this sequence in terms of electrical test procedures doing the tests. This next slide here shows us an example of engineering model tests. You can see here it's a very simple, the spacecraft is full scale, the some of or most of the electronics are installed or just a side of it, but all the cabling is connected to the subsystem. So because here I'm concerning to make the electronic test of spacecraft, I'm going to check if they work properly, even though they are not flight approved. I'm not concerned about that. I'm concerned only to see if they fit in their compartments, if they are correctly interconnected, if they operate properly, if they talk themselves properly. That's the main goal of this tests in this engineering model. The tests to be performed in the radioelectrical model. The objectives are we have to verify the effectiveness of the shielding of the structure. We also do a characterization of the layout of the structure and antenna positioning. And also we verify the suitability of the main specific layout. So what we do, we put spacecraft inside a anechoic chamber. We must have this in our laboratory. We put this spacecraft, you can see here, it is just the structure with the empty compartments. Now we do analysis of how one compartment is shielded against the other one, how the antennas are positioning, they can communicate, some disturbance from the structure. So that's the main idea to do this kind of testing inside the anechoic chamber, to verify how the antennas and compartments are shielded among themselves, if they work properly in the real situation of the spacecraft, not only designed on paper, on a computer. Okay? So the anechoic chamber will have wave absorbers in the wall, will be shielded chamber as well, walls to avoid any interference from outside, and the wave absorbers to avoid multi-reflection that could disturb the analysis of the radioelectrical model tests. Okay, mass properties measurements are very important because the launch vehicle, the launch procedure, they requires a precise knowledge of the physical parameters of the spacecraft. If this can be measured in the laboratory, you can do this in the laboratory to get these numbers. There are numbers. And these measurements, they can include the mass of the spacecraft, the center of gravity of each part of the spacecraft, the main spacecraft and part of the spacecraft as well. Other important information like the moment of inertia, the product of inertia, sometimes they can do that as well. And in case of the spacecraft works in a spinning mode in space, we also have to do a balancing of the spacecraft. All these measurements and numbers are very important to give to the people from the launch vehicle, because they can program their launch vehicle, because they know exactly what's inside their rockets, the mass, the center of gravity, to put the spacecraft in exactly the correct orbit and angle inclination to get the orbit, and the altitude correct. They need this information, so we have to get this information in the laboratory. We call mass properties measurements. We get numbers, and we give these numbers to the people from the launch vehicle to make sure they put in the right orbit. Here's a picture of a mass property measurements of a satellite from NASA in Argentina, CONAI, during a test in laboratory. Here is set in top of a torsional pendulum in a center of gravity scale. So we get measurements from this scale here to give the guys of the launching vehicle to get the proper orbit of the spacecraft. This is just an example doing the measurements. Okay, alignment measurements. These are very critical because the spacecraft is going to be orbiting, and normally it needs to be facing something, or for communication needs to face the antennas to some points in the ground, or if it's going to carry cameras for imagery, so they make sure the cameras are looking to the ground and not in an angle to another point. They don't want that, they want to look to the ground normally. Or for the scientific sensors, they want to look into space, so that means we need the spacecraft to be flying in a proper attitude in space. They must be positioned correctly in space. How we do that? The spacecraft has sensors. They have sun sensors star trackers and earth sensors, for instance. So using these sensors, we can tell the spacecraft what's the exact position it's flying. It's not bent like this or the other situation. It's right the correct attitude of during the orbit. So they use sensors. So if they have sensors installed, we want to make sure the sensors are installed properly in spacecraft. Because they are installed with an angle, wrong angle, they can give wrong answers for the position of the attitude of the spacecraft. So before sending spacecraft to space, we have to make sure the installation of these sensors are made correctly. How we do that? We use special equipment I'm going to show later on, but also another kind of alignment we need is like the thrusters. The thrusters, the power to put the spacecraft in the right position. So install thrusters, small rockets on the spacecraft. We need to, when we fire them, we have to make sure that they fire in the right position, direction. To do that, we have to analyze and measure the direction they are installed. Antennas and reflectors are the same thing. If we understand the antennas are looking to the ground at a certain point, we have to make sure they were installed according to the design. So they are attached to the structure, and they have the reference of coordinated spacecraft. We have to make sure they are installed correctly. How do we do that? We use theodolites to do that. We have some mirrors installed on the spacecraft. These mirrors are connected to the place, the sensor or the antennas or the device that require alignment. So use 3 or 4 theodolites and do a kind of several triangle analysis. We can tell exactly if those sensors and or other instruments are installed in the correct expected position on the spacecraft before flying. So we make sure they are going to read the right position. So use theodolites for this purpose. Okay? We can do this by using several measurements of spacecraft to get the right measurement and position of the spacecraft, make sure they are installed correctly. We call mass properties and alignment measurements. We call alignment measurements. Okay? Okay, let's talk about the electromagnetic interference, electromagnetic compatibility tests, EMI/MC tests. So recall that the spacecraft has several equipments, a large amount of equipment installed inside of its structure. That means that it has some situation that several of them can be operated at the same time during the flight. So with this, there's also a risk that one equipment can impose some kind of electromagnetic interference to the other equipment right next to him. So to analyze the risk analysis of that, to verify if this can happen, what we do, we put the spacecraft inside a chamber, what we call anechoic and shielded chamber. Shielded chamber because it's made out of metal, so that means any electromagnetic interference coming from outside the chamber will not go inside of the chamber. So there's no interference from outside to inside. I can do a very precise test inside the chamber. And also this particular chamber is covered by a special foam. The ceiling, the walls, and the floor with a special foam that can absorb the electromagnetic waves hitting the surface. So that means I have no bouncing, no reflection inside the chamber. So that means it's very similar to what's happening in space. So the electromagnetic signals goes off away from the spacecraft, does not return, does not bounce back. So I can do a very precise measurements if I have any kind of interference from one equipment to another equipment. So that means that during the test, if I found a small noise, electromagnetic noise, I'm sure that this noise is coming from the spacecraft itself. So it's better to do an analysis like this, try to correct the problem. So with doing this, we can demonstrate that the spacecraft is electromagnetic compatible with itself and also with the launch vehicle during the launch phase. That's the test we do, EMI/MC test inside anechoic and shielded chamber. This next slide shows us an image of a spacecraft inside the anechoic chamber down in Brazil, in this particular case here. You can see the walls are filled with those blue wave absorbers. The scene as well, the floor at this moment is not covered, it's going to be covered during the tests. So here we can perform electromagnetic interference, electromagnetic compatibility tests of the spacecraft. Okay? To see if I can find any noise inside spacecraft that can interfere with operation with other equipment inside the spacecraft. We don't want that. We want that all the equipment operate properly without interference. We can do the testing in the ground like this before sending it to space. Okay, let's talk about vibration tests now. Vibration tests, as I said, are very critical because they have to prove that the spacecraft will survive during the launch phase. So typically we perform vibration tests in two main modules. We do tests on the qualification module, and there what we do is we collect data of the behavior of the structure during the vibration and shock loads. We get data from that. Doing that, we can qualify the design of the spacecrafts. And because we use a margin, we do a better qualification. We vibrate more than expected during the launching phase. But in the flight module, we also do vibration tests. But here is because the flight module, we just confirm the adequacy and capability of the structure design of spacecraft. We qualify the qualification model. Here we do just the acceptance of the spacecraft. And also important, we demonstrate the workmanship requirements have been met when the spacecraft is under all the vibration and shock strengths. Why? Because one thing is design spacecraft, another thing is manufacturing it. So technicians will use their hands to tighten the bolts, to install a resin spacecraft, so that means they can make mistakes, make error. So it's good to verify this even if the qualification model was approved. Now I have another satellite made for different people sometimes. We make sure this manufacturing was made accordingly. So we do another test over there. So how we do the vibration test? How is it set up? So now we install a significant number of sensors we call accelerometers. Let's say, for instance, 200 accelerometers are installed in spacecraft nodes. Okay, why nodes? Because the design of the structure of spacecraft, those guys know the critical point of spacecraft will vibrate more, can be critical, that can be damaged. So we put sensors in those points and they do the vibration, get data from those points, and then the design compare the real data that they get from the tests and the expected numbers of vibration they obtain from the modeling. They compare this to see if this is reasonable. So then we put spacecraft on top of a shaker, a vibrator, or in a horizontal sleep table. It's a machine that do vibration of the spacecraft. So we do all the connection of this cabling, these sensors installed on the spacecraft. And then we program the shaker with the vibration curve that the guys from the launch vehicle give us to the laboratory. They know exactly the level of vibration, the G's against the frequency. We have this curve, they give it to us, we program this in the computer, we make it vibrate very close to what's going to vibrate during the launch phase. We put a margin, a little higher vibration to make sure it's well tested in the laboratory here. That's the setup, that's preparation for the test. And the sequence we go, first we do a signature of the test. It's a very low level, we vibrate in a very wide range of sine run, from let's say from 5 Hz to 2000 Hz. And we get the response of the structure in all the 200 points of the spacecraft. We know how the spacecraft vibrating in different kind of frequencies. We got this we call signature. After that we do a real sine sweep vibration on the spacecraft, a higher level of vibration. After that we do a random vibration spacecraft because they can analyze the real situation of vibration spacecraft. We do random vibration, high level vibration, sine and random. And after that we can also do another signature low level. What we do, we have the post big vibration, we do a signature again, and we can compare the two signatures. They must be equal. If they are different, that means that something changed inside the spacecraft during the vibration tests. This is no good. Some kind of bolt was detached, something like this, or some kind of material was bent. So because they present a different performance and behavior if they have modified during the test. So that's important of having a signature to compare prior to the test and after the tests. This is the way we do the vibration tests. Here we have a picture of vibration test. You can see here the spacecraft set on top of the shaker. Here is going to use the z-axis of vibration, not necessarily the z-axis of the spacecraft, but z-axis of vibration. We put spacecraft in there. We can see roughly all the red cabling coming from the spacecraft. They are the sensors of vibration sensors. They are connected to the data acquisition system. There we can record the level of vibration for each part of the test of the spacecraft. You can see the shaker, the sleep table, and the axis of vibration. I'm going to show here a quick video showing vibration of the spacecraft. In this video you can see starting the shaker of the spacecraft, in this particular case in the horizontal mode, sleep table. It starts with low frequency and slowly going to higher and higher frequency. You can see the shaking. If you see this vibration testing in person, it's very, very high vibration level. It's impressive because a large structure, like say 3 or 4 tons, vibrates in front of you, so it's very big vibration. So this is the real vibration the spacecraft is going to face during the launching moment of its lifetime. So it must survive this vibration. The structure must be stiff enough to survive this mechanical condition of vibration and shock. Okay, let me talk a little bit about the acoustic tests. The vibration tests performed on the shaker, they are the classical ones because they are applied to represent the vibration coming from the structure of the rocket itself. So because the spacecraft is set on top of the rocket and with a kind of belt attached of the two parts, the spacecraft to the rocket, once the rocket vibrated from the burning of the fuel, the structure of the rocket also vibrated and consequently the structure of spacecraft also vibrated. This is one thing of vibration, that's what we just saw it, okay? But besides of that, apart of that, we also have another vibration on top of the spacecraft. The top part of the rockets, the fairing of the rockets, while the rocket is hitting this atmosphere with high speed, we have a lot of shock with the atmosphere, and then this shock will produce a lot of acoustic vibration on top of the spacecraft because I still have some gas inside the fairing. So if I have some gas, some air inside the fairing, they can transmit acoustic waves from the top of the rocket to the spacecraft. So then I have another kind of vibration to the spacecraft. Now I'm talking about acoustic waves on top of the spacecraft. So we have to test that. How we do that? We have to have in laboratory acoustic chambers. So the acoustic chamber, they have some big horns on the top of the chamber. They are just a room, a big room. We put spacecraft inside this room. Those horns, typically they are powered by a flow of nitrogen gas. Very precise. We use 3 or 4 horns, different size, large one, medium one, and small one, powered by a flow of nitrogen. And when you have a flow of nitrogen, you can produce noise. And then you have 3 or 4 horns, different size. Using computers, you can program the flow of the nitrogen passing to these horns, and you can reproduce very close the curve of the acoustic noise is going to take place during the launching phase. The guys from the launching vehicle, they know exactly what's the noise their rocket will produce on top of the spacecraft. We can reproduce that noise in the laboratory using acoustic chambers. So how we do that? In the qualification model, the objectives are to submit the spacecraft to this acoustic field inside the chamber. Then we qualify the design of spacecraft under this acoustic noise of the launching. because the fairing is vibrating to the, against the shock to the atmosphere. In the qualification model, we can obtain and provide additional information to the design of spacecraft. But on the design, on the flight model spacecraft, we do the test to confirm. Now we want to confirm the adequacy and capability of structural design of spacecraft, because we already do the qualification. Now we do the confirmation only. And also, as before, we are going to verify the correctness of the workmanship of the spacecraft. Once more, different people or different situation, or another time we are going to start to build spacecraft, we can make small mistakes. We have to test the flight model again, even if you have tested qualification model, because people work on spacecraft, we do different jobs, we will make sure it's done properly and correctly. That's why we do again the flight model test. So how is it set up? Again, we install the sensors on the spacecraft to measure the vibrational level of each part of the spacecraft. Could be exactly the same sensor we installed for the typical vibration sensor test we did before in the shakers. And then we put spacecraft inside a cart, inside the chamber. But now here, because we are talking about acoustic tests, acoustic waves, we also install microphones around spacecraft. Why microphones? We have acoustic waves, we need microphones to measure them. We want to make sure that the level of acoustic waves, of acoustic noise are taking place exactly the way we want the level of noise to be reproduced around the spacecraft. These acoustic waves must be the same of the ones coming from the real launch from the rockets. So then we measure this with microphone. We can install, let's say, 8 or 10 microphones around the spacecraft to guarantee, to ensure the level of acoustic waves are arriving at the spacecraft as expected. And the 200 sensors are used to analyze the response of the spacecraft, how the spacecraft is going to vibrate after the input of the acoustic waves. Okay? As I said, we program the horns with the curve of the launch vehicle plus the margin. So this sequence is about the same as we did before in the shakers. We do a low-level signature test, we see the response of spacecraft, we do the intermediate test and the proto-flight level test. We can go up to over 140 dB, it's a high level vibration. And we do again after that another low-level signature test to compare before the test and after the test if something changed inside the spacecraft. If you got something different, I know that something has changed inside, I have to look for that, I have to analyze what happened inside spacecraft during the vibration tests. Okay, this is just a picture showing the acoustic chamber. You can see here inside at the right, the spacecraft installed inside a cart. The technicians are preparing the test. You can see around the spacecraft some stands holding the microphones where are going to ensure that the level of vibration took place during the tests. Okay? Again, the spacecraft has a lot of sensors installed in their structure to measure the response, the results of vibration in the spacecraft. Okay? And in the top of the chamber you can see the horns. Also on the left side you can see the horns. The 4 horns, the low frequency big one, the mid frequency mid average size, and the smaller one for higher frequency on the top of the chamber, right? We can produce the level of noise using these horns on the top of the chamber through the use of a flow of nitrogen. We flow from the top and have exhaust on the bottom, so the nitrogen just flows inside and produces vibration.